Standard enthalpies of formation provide a convenient way to calculate an enthalpy change for a reaction. So, in this particular case, we have methane plus oxygen combined to give carbon dioxide and water. And we are going to calculate the enthalpy change for this reaction using this little formula, which says that the enthalpy change for the reaction equals the sum of all enthalpies of formation as long as we multiply by the number of moles for each component. And I'll show you what I mean by that right now. So what is the first component? Well, we have methane. So CH4 gas. And what is the enthalpy of formation for methane? Well, we can look that up in a table, and here's one that I prepared earlier. And it gives the enthalpy of formation as negative 75 kilojoules per mole. Kilojoules per mole. Now remember, this is an enthalpy of formation for this reaction. Carbon solid plus 2 moles of hydrogen gas give carbon dioxide, sorry, not carbon dioxide, methane. Let's do this correctly. Methane gas. In this particular reaction, so the reaction of formation, methane is a product. In our reaction, methane is a reactant. That means that we need to change the sign for the enthalpy of formation. So negative 75 becomes positive 75 kilojoules. And that holds true for all calculations of this sort. The enthalpies of formation for your reactants have to have their sign reversed. So if the enthalpy of formation is positive, it has to become negative. If it is negative, it has to become positive. Let's move on. Next one is oxygen. So the enthalpy of formation for oxygen is 0 kilojoules per mole. That is because oxygen gas is the most stable form of oxygen element at 298 Kelvin or 25 degrees Celsius and 1 bar of pressure. So in this table we can see the enthalpy of formation is 0. Next component is carbon dioxide. So now we are looking at our products. So carbon dioxide gas. The enthalpy of formation for carbon dioxide gas is given as negative 394 kilojoules per mole. Once again, that is the enthalpy of formation for this particular reaction. Carbon plus oxygen gas gives us 1 mole of carbon dioxide gas. So in this reaction, carbon dioxide is a product, and up here, carbon dioxide is a product, which means that the enthalpy of formation can be used as it is. So generally speaking, when you're looking at enthalpies of formation for your products, if you're using this particular formula, you can use the enthalpy of formation, the value for the enthalpy of formation as is. Let's move on. Water. So H2O, liquid, delta H. Sorry, the standard enthalpy of formation for water is given as minus 286 kilojoules per water. And make sure that you are actually looking up the enthalpy of formation for liquid water and not for water in its gaseous state or in its solid state, because the enthalpies of formation are different. Now, the next thing that you have to be careful about here is that there are 2 moles of water. That means that we will need to multiply this value by 2, because for 1 mole of reaction, if you wish, we need to take into account 2 moles of water. So it's going to be 2 times 286 kilojoules per mole, which gives us negative 572 kilojoules per mole. So those are all of our components, and now we just need to add them up. So our enthalpy change for the whole reaction equals the enthalpy change sorry, not the enthalpy change, the enthalpy of formation for methane, plus the enthalpy change for oxygen. And you could argue that I need to multiply that one by 2 as well, because there are 2 oxygens in this reaction equation. However, seeing how the enthalpy of formation for oxygen is 0, 2 times 0 is 0, so it will not make a difference. Plus the enthalpy of formation for carbon dioxide, plus the enthalpy of formation for liquid water, multiplied by 2, because we have 2 moles of water in this reaction equation. Now we can put in the values. So, for methane, it was plus 75 kilojoules per mole, plus 0 kilojoules per mole for oxygen, multiplied by 2, plus negative 394 kilojoules per mole for carbon dioxide, plus negative 286 kilojoules per mole for liquid water times 2, because we have 2 moles of water in this reaction equation. That will give us a value of, and I can use my calculator up here, so we have 75 plus 0, so I can ignore that, minus 394 minus 572, because that is 286 times 2, and we get a value of 800, negative 891 kilojoules per mole of reaction. So another way, we have calculated the enthalpy change for 1 mole of this reaction. 1 mole of a balanced reaction, which includes 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water. Now, if you're worried about all of this flipping of signs, plus to minus and minus to plus, there is another equation you can use, which many people do use because it's a little bit easier, and that is this one. It is pretty much the same thing. So it says that the enthalpy change for a reaction equals the sum of the enthalpies of formation of products minus the sum of the enthalpies of formation for the reactants. So let's do that for our equation, just to show you that it is the same thing. So what are our products? Well, we had carbon dioxide, so we'll have minus 394 kilojoules per mole, plus water, so it's minus 286 kilojoules per mole, but there are 2 moles of water, so we need to multiply that by 2. So these are the enthalpies of formation for our products. And we need to subtract it from the enthalpies of formation for our reactants. And what are our reactants? Well, there was methane, so that was minus 75 kilojoules per mole. So in this particular case, when we're using this formula, we can use the enthalpies of formation as they are. We do not need to flip the sign. So up here we saw that the enthalpy of formation for methane is minus 75. So we can use that value as is, as long as we are using this particular equation. Plus, the other component is oxygen. That's 0 kilojoules per mole times 2. So these are the enthalpies of formation for our reactants. And now we can go down here, equals. So we'll have negative 394 negative minus 572, and that gives us negative 966 kilojoules per mole, minus the sum of all the reactants. Well, it's just minus 75 kilojoules, and a minus gives us a plus. Actually, let's do that step by step. So it's minus 75. Hold on, let's keep the color. Minus 75 kilojoules per mole. Minus and a minus become plus, which means I can go negative 966 plus 75, and that should give me 891 again, and it does. So it's minus 891 kilojoules per mole. So the answer is the same. So to recap, if you decide to use this particular equation to solve your problems, you have to make sure that you've changed the sign for the enthalpies of formation for your reactants. So a negative enthalpy of formation will become a positive, and a positive will become a negative. If you're worried about stuffing that up, then I suggest you use this particular equation to solve your problems. There you can use the enthalpies of formation as they appear in the table.